So that's sort of the context of site-specific weed control. Then how does it fit within, I guess, the site-specific weed control system? And this is, I guess, how where the owl and sort of how it all emerges within this kind of ecosystem of different types of technology. And the site-specific weed control system is made of a few components. I've used this slide a few times, but I sort of like the way it kind of describes how it all fits together. And the sensor is almost what I talked about before. We had that emergence of technology maybe 50 years ago with the weed type detection systems. And that is already reflectance or fluorescence-based sensors. Then you have imaging sensors like cameras and distance, maybe ultrasonic, I know has been used. And then you have some sort of processor that's connected to that. And the processor has some sort of weed detection algorithm that's connected to it. The processor might be a simple microchip, or maybe it's a whole Raspberry Pi computer, or an Arduino, or some other sort of Jetson platform from NVIDIA. But once you have the weed detected with your algorithm, then you have the controller that makes the decision to deliver that. And in the case of herbicides, the control delivery is probably a solenoid, maybe one of the T-Jet chem savers that you pay almost $400 for. Or perhaps it's, say, a hydraulically activated tine, and maybe you're controlling some hydraulic solenoids. But you can swap in and out each of these different parts of the system. You can swap the sensor out for a camera. You can swap the processor out for another open source board that's not the Raspberry Pi, like a BeagleBone. But what it kind of shows here is lots of these things are quite plug and play. And that's what we've tried to sort of do with the OpenWeedLocator approach is we can swap in and out different cameras. You can swap in and out different detection algorithms and different solenoids and sort of control delivery on that side, if you don't necessarily want to spot spray every time. So the sensor-based algorithms, or sensor-based systems that I mentioned, they're really just almost a 2-pixel kind of sensor, or wouldn't say a camera. So they're not really camera spraying when using a weeder or a weed seeker, or those reflectance or fluorescent-based devices. Because what they do is just use the difference in wavelength between, in this part of the spectrum, say red and near infrared, and they use that difference between soil and sort of dead vegetation and healthy vegetation, which often reflects strongly in the near infrared, compared to where it absorbs strongly in the red part of the wavelength. So visual spectrums from about just over 700 down to about 400 or 450 nanometers, and reflectance is just how much light is given back. And so what you can do with these sensors is quite smart. You can compare that and see whether there's a living thing below. They use fluorescence, which is slightly different because you shine a light onto the plant and then you look at what light comes back. But the idea is quite similar in that it's not camera, in the sense you don't have any spatial awareness of what's there. You just have these spectral awareness, I guess, of what's being reflected by the plant. And in this case, the algorithm might be some proprietary algorithm behind there determining where or when to use or detect a plant. But then I guess it's more basic in that sense, but highly effective. It does the job it's designed to do. The cameras, you can kind of think of them as like those individual pixel sensors just on steroids. So a 12 megapixel camera has 12 million pixels, which is like 12 million of those sensors combined together on an array that is the size of a maybe, I don't know, 50-cent coin if you're from Australia, or like maybe a couple centimeters by a couple centimeters in their largest formats. So you think of the ones on your phone, they're almost microscopic sensors, and they pack all these different pixels and these different sort of individual sensors onto this one larger array. And these digital cameras generally have 3 channels to them. There's the red, green, and blue channel, and people can modify those to, say, be more sensitive to the near infrareds, and you can play around with them quite a bit. But the default is for the RGB channels. And with this, you can start to sort of peel apart some of the information behind it, and then start to design algorithms to detect these plants. And as you can see here, this is the original image in color and replicated 3 times. But then down the bottom, I've split it into the red, green, and blue channels. So you see the green channel is quite bright because, well, wheat and the wild radish underneath it is green. And then what you can do further is actually look at the underlying pixel values. And so this is what the computer would see. Each of these numbers is a number from 0 to 255 when you're dealing with an 8-bit processor or image. And this will show us how bright that part of the image is. And this is what computers have to deal with when they're trying to detect a weed, in essence. And so when you give it enough training data for these more advanced algorithms, where rather than just detecting green, you actually have an algorithm you train, you give a lot of samples. It's just trying to pattern match across all these vast arrays of numbers on many millions and millions of pixels. And it always blows me away that this can be done in real time, and you can actually teach algorithms to detect what is a wild radish in this blur of numbers. It's quite impressive. So that's the camera. And of course, that was the sensor part, and the processor part is sort of embedded in there somewhere. And these are the different use cases you can come across. So it's not always spot spraying. This is one video I really like, but it's targeted tillage demonstration from up in Narrabri in northern New South Wales, about 7 hours north of Sydney. And this is some work that my old supervisor, Michael Walsh, did to develop the targeted tillage platform. But as you can see, the sensor, in this case, is a weed it. It's triggering a hydraulic solenoid to come down and chip out these volunteer cotton plants, or that windmill grass, Chloris virgata, I think. And you can see the sensors just at the top here with the red light coming up. But you could replace that with an hour, you could replace it with other cameras and do fancy things. There's, of course, spot spraying, which we all sort of know and love. And this is a system in Argentina from Deep Agro. And they're doing, they're basically similar to what the weedits were doing in those previous images. They're doing just detecting of green, these plants here on a fallow background. I think it's some old corn. And that was in Argentina. And they're a great company doing some really cool stuff down there. I guess that is two different use cases. So it doesn't have to be spot spraying when we think of image-based or weed detection. So what are some of the opportunities? Well, I guess the question is, well, what would you do if you knew the location and species of every plant in your or a field? And it then sort of raises questions, well, would you always control it? Or maybe the first level is you spot spray the weeds and then blanket apply as like a reassurance of something else in case you miss some. But maybe the next level up is if you're more sure about certain species, you can spot spray the ones are quite problematic, and then you could do the blanket on the rest. So you could sort of spike a mix and then blanket everything else. And then maybe you can do species plus growth stage or size-based detections. Then you can adjust rates on the fly, doing a range of different. This is where you start to get tricky sort of nozzle setups. It gets more complicated, but you can potentially then start to do more fancy things with weed detection. So you move away from simply just detecting weeds and being site-specific weed control to being almost like plant-wise weed management, where you make decisions on the fly in the real time about every plant that the camera is seeing. And then perhaps at the very end, this sort of fourth level that I see is where you have species spot spray plus rate plus resistance prediction, maybe if you've been there before and the plant is still around. And then you have multiple options about different lines and all that sort of thing. But then we sort of get to open source benefits. I guess don't spend too much time on it, but I think open source is really the fundamentals of the OpenWeedLocator, and I think it's something that I've learned from a lot. I think I value it significantly because it helps the industry move forward faster, and it's all about sharing the tech recipe, because it means all these sort of ideas we have previously on how to use these detection algorithms, maybe at different levels of complexity, we can start to iterate on them faster by developing, I guess, on what other people have done before. So if someone else comes to the market, they don't have to start from scratch in developing these new products. And that might come from, say, broad scale collection of open data, or maybe it's more hardware based and open sourcing the hardware, like I've sort of done with the OpenWeedLocator. And people can iterate that onto a whole range of different platforms and not just necessarily spot spraying with 4 different nozzles. But this brings us to the OpenWeedLocator. And so it started out as, I guess, an educational or practical tool to kind of look at, for me, it was to learn to code a little bit back in Python back a few years. It is all about doing simple weed detection, so color-based, now with a bit of model-based detection as well, although, sort of still on the fringes. And it was meant to be simple, low cost, about $400. People can 3D print the enclosures at home and get sort of better access to this technology. And it's, I guess, come away since then. This is the, as you can see, one of the older versions. This is the image, I think, from the previous demonstration. I can update this now. But you can see it's all laid out in a flat sort of iteration. And the software design is quite straightforward too. You give it the image, you break it, as I've said previously, into sort of its composite channels, so RG and B. And also you have a different color space as well called hue, saturation, and value. But you can basically break an image up in a number of ways. And then with these, the software with these sort of data, I guess, into the form of images, you can then start to run a few different algorithms like XG, which is a very old one from the 1990s. And then you can do normalized, or you can do combination algorithms like we have done, to then give you an output, as you can see here, which is the weed being detected. And this is, I guess, the most basic part of the software. There's a lot of other complexity in sort of managing how you detect and actuate each of those different channels. And then this next diagram is how the hardware sort of integrates with that software. So you have the frame comes in, you run that algorithm sort of here in this arrow, I guess. That's where the sort of controller, the processing happens. Then you go to the zone allocation. So where in the image is that weed located? And you actuate, say, zone 1, 2, 3, or 4. Each of those zones corresponds to a particular pin on the Raspberry Pi, which then corresponds to a relay, which then can be actuated to turn on a solenoid. But the best thing about it is all of these can be actually modified. So you can have a single zone, as I'll show in the demonstration. And you can also have like 4 or 5 or 20 if you want to. It's limited by the number of GPIO pins you have and the number of relays you can connect. But people have often asked if you can put it on designs, say you don't necessarily need 4 zones, you just want 1, and that's sort of changeable with a simple changing of a variable in the code. And then it just assigns it to the lowest GPIO pin. But now some of the exciting things we've done recently. So that was all the old part of it. The official hardware was launched with a lot of help with my brother, Patrick Coleman, and he's a big fan of open hardware. I guess maybe I'm inspired by some of the work he's done previously. But this is the new OWL driver board. So you know how we, I guess, talked about having all those different relay boards and everything sort of needing to be connected, and all these different parts, I guess, are part of that image. That's almost being combined into this board here. So we have a power supply on this board now that will take anywhere from, I think, 6 to 27 volts. And that will convert the 27 volts or whatever down to the 5 volts for the Raspberry Pi. They'll also provide, I think, up to 3 amps. But anyway, enough to power the Pi and some peripherals. And then you have the outputs here too. So each of these is a 12 volt, 2 amp rated output. You can connect your solenoids to. So basically combines it all into one. As I'll show you in the assembly, it simplifies a lot of the work required to assemble these devices. You just have a 12 volt input you can provide, which is quite straightforward. And we just added, I think the other day, another pin here, based on some feedback from a farmer in South Australia. He was suggesting that if you could control or enable or disable each of these outputs based on, say, a section control relay on your sprayer, then you could almost integrate it with your GPS. And so that way you can do more selective spraying, I guess. It also means you can control the outputs of the OWL more easily as well. So you can turn them on and off, say if you're going around a headland or parts you've already sprayed. So this is an older photo, I guess, from 2 weeks ago, 3 weeks ago. Now there is actually a 6 set of pins here that can enable and disable. But again, I'll show that in the assembly. The other part is the OWL enclosure. So this is a rugged aluminium enclosure, which I guess I've been working on to try and make the OWL more useful when out in more rugged conditions, say on the back of the sprayer. And so I'm currently about to order a set of these from China. So hopefully, if you do interested in, or if you want to purchase this board, you can from my brother's website down here. I'll also send out links, I think, after this event with the links to this. And this, I should have opened an online store that my brother haven't had time to. So you potentially buy these in the future. And again, I'll send a link around to those, or send me an email if you're interested in purchasing them. This is a demonstration of it on robot. I think I've shown this a few times, but just to, I guess, show it does work. This is the older version from a couple of years ago, and it's since improved significantly. But that's just a boom, a 2 meter boom. There are 2 open weed locators on that boom. And as it's picking up each of those green weeds on a fence line, it's not an Agarus robot, but you could easily put this in the back of a ute. Then it's sort of spot spraying it and turning on each of those nozzles and solenoids just there. So I guess one of the biggest things about the owl is the community behind it. I know we've got people from all over the world who are building them. I think it was 8 countries last time I checked. And it gives a whole range of perspectives on how to use the owl and how to make it better. So it gives you a much more, I guess, more robust potentially tool, because more people are giving it feedback and using a range of different ways. Now, this is, I think, Stephen Mervine of Mervine Robotics over east. I think that's his robot. I think you're probably working on an improved version at the moment. There's a guy in Canada. I think there's some guys in South Australia. These are a couple of our versions. I think it's up in Tamworth. This is a robot over in Denmark that I mounted it to, the Agro Intelli robot. But it is quite very, yeah, it can work in a number of different platforms, I guess, is the purpose of this, so it can be more adaptable. And then onto sort of the past, present, and the future, we've got, as I mentioned before, the past owls were quite slow. They're running for 60 to 30 frames per second at about 416 by 320 resolution, limited functionality, green on brown only, and a whole ton of parts that had small wires that could go wrong. Now we're looking at about 60 frames per second at 640 by 480 resolution. So that's from both improved code and also the Raspberry Pi 5. So if you run it at the original resolution, you end up with about, I think, 130 frames a second on the Raspberry Pi 5, which is, given the camera, I think, is limited to 60. You're basically double processing every frame, which doesn't give you any benefits. We're now got this more rugged enclosures. It's easy to use. We've changed the way, I think, the config files and all that work. So that's where we're at now. In the future, we're looking for, I guess, larger platforms. How can we make the owl more usable, user-friendly across, say, a 12-meter spray boom or 24-meter, but also making sure it's easy to sort of add and assemble on, say, like a 4-meter fire break or spray fence line spray boom too. Also, so that part of that equation is in-cab control. Then there's the green on green, so running more complex algorithms than just green detection that I mentioned before. And so that includes things like high-low AI, which we just released with the Raspberry Pi AI kit. So giving that a go if that works. But otherwise, you can get about 20 to 30 frames per second using the OpenWeedLocator. Sorry, using the Raspberry Pi 5 just by itself and running YOLO algorithms on it. So there's a range of different options there, I think, for us to run green on green, either with extra hardware or just if you're running, say, lower speeds, just with the Raspberry Pi itself. And always looking to make it easier to assemble and use, of course. So firstly, the different parts we have. So we have the 3D printed components that are essential, I guess. The screwdriver. You need the, this is the tray that it sits on. And then the tray also has this holder for the lens. So these are the 2 essential 3D components. If you're using an aluminium enclosure like this one, the only 3D printing you need to do is this, or having someone else 3D print it for you. If you're doing a 3D printed enclosure, you also need a 3D print this, which is just replicates that aluminium extrusion. And you also need to 3D print an end cap, which also has a glass lens in it as well for, I guess, to keep all the water out. This is, there's 2 pieces here. So you print that first and then you lock it in, and then you print this other end piece, and then you mount the lens inside of that. The lens is designed for is one of these 37mm K&F concept lenses, just because they have a really nice sort of anti-scratch coatings, waterproof, and they also stop UV as well. So I think you do end up with a much clearer image. Then on the back is just another end cap. And you do need to put some foam in here, so just a rubber bead, and that presses up against the edge here to make sure there's a nice seal. I think once someone, Helga, pointed out that these are actually not 45 degrees, which I should have probably noticed, and I'm in the process of fixing. And you also note that this design is slightly different to the one on the repository at the moment, and I'll be uploading that. Again, a suggestion from Helga about supporting the lens as opposed to having it freestanding on the enclosure here, so it doesn't, sorry, on the tray. So that way it's better supported, I guess, for longevity, which makes a lot of sense. So in any case, that's the 3D printing done. The other thing to mention is on the back here, you do have these options to mount the camera module 3, which is a sort of much smaller form factor that can fit, and there's another 3D printed component that will fit on top of this that can then mount that camera module 3 too, with a lens sticking out the front here. So there's a few different camera options as well, although we stick with the global shutter, because you get, from what I've seen anyway, we haven't done any standardized tests yet, but just anecdotally is that this has a better image quality compared to the Raspberry Pi HQ camera, or certainly the V2. V2 is quite a terrible camera option. I wouldn't recommend using that for this purpose. So that's how the Raspberry Pi global shutter comes out of the box. We also use, or it's designed to work with the 6mm CCTV lens from Raspberry Pi as well. That just gives us the right field of view when mounted at 1.2 meters above the ground. So 1 meter wide to run 4 25cm nozzles. But of course, you can change the lens over or change the mounting height depending on the situation. So I guess the first thing I do usually is probably sort the camera out. So this is straight out of the box. This is how it comes. There's a few different things you need to remove from here. The first is this adapter ring. I know this has always got me the first time I did it, and that adapter ring will mean you can never actually focus the camera with this lens. So it's a C to CS mount adapter, which you don't need. So if you remove that, I have far too many of these lying around, and you can actually see the sensor. That's the imaging sensor underneath there. You don't want to get any dust or dirt on that, so I always try and keep it facing down. So the next step is to attach the lens. So if you unscrew the lens cap, again, you want to avoid getting any dirt or dust on that, otherwise it will always show up in your images. And then tighten that down on here. And you want to screw it all the way in so it's nice and tight and can't go any further. The next thing you want to remove is this mount. So this is for the, I guess, the camera to be mounted on a tripod. We don't need that, and it gets in the way of the enclosure. We can also need to remove this cable. So if you're running a Raspberry Pi 5, which is this Raspberry Pi here, you need a different cable because it goes from a standard to a mini size, which is, I think, a 15 to a 22 pin MIPI cable. And so to fit in these sort of spots just there. So if you're using a Raspberry Pi 4, you can just stay with this. You can just stay with this old cable. But I've got a Raspberry Pi 5 here, so I would recommend using a Pi 5 if you can. But a Pi 3B Plus will also work in case you didn't want to. Because the Pi 5, I think, is a bit more expensive. Let me just open this up. Remove that, and we'll install the camera cable later. Now to take out the tripod mount. Sometimes they're a bit stiff. That's that out the way. So that's the tripod mount. If you do want to mount on a tripod, of course, you might want to keep that. And then we're away. The other part to point out is this little flathead screw here will lock this ring in, which is worthwhile doing once you've got the focus. So this is the coarse focus focal ring, and then the other is the fine. You also have the open and closing of the aperture, which is, you should be able to see I hold it right, you can see that opening and closing potentially. But of course, you want it open all the way to get most light in possible, so we can have the maximum or fastest shutter speed at all times. Then we'll do the focusing at another point, but you want to sort of wind this out probably a few millimeters out from the base, just about, to get it to the right point for the rest of the focusing when you want to define focusing later. And then once you're finished, you of course want to tighten that down. Now, to mount it to the tray, you want to mount the camera first. I've made the mistake of mounting the Raspberry Pi first many times, but you do need to access these two holes down here to lock it in place, which will be obscured once you have the Pi in place. So you want to put the side with the camera cable facing upwards, and then just sit it in that tray like this. I should mention, sorry, I have also already added these standoffs. So these are brass standoffs. As long as you have enough clearance on this plastic backing, I think these are about 10 mil ones, but you can get much shorter ones, but just make sure that there's enough clearance between the backing and the plastic plate here. So these are a pain sometimes to install, so I've done you the service of not making you sit through me and my shaky hands installing those. So once that's seated there, you just want to use some of these I think 2.5 millimeter screws or whatever comes with your standoff kit. I'd recommend using a standoff kit like these. They come with a range of different standoff options, because these are the ones you use for the Raspberry Pi base. These are for the camera, and then also your nuts and your screws to fit. I also use nylon ones sometimes as well. I prefer, I think, brass just for longevity, and the nylon screws tend to strip much easier, particularly if you want to tighten it down hard so it doesn't come loose. Anyway, use the screws to tighten it in. Almost on the bottom. All right, make sure it's tight. The bonus of having this new locking lens locking feature is that it will make sure the camera stays in place instead of just having those 4 screws there. So it's quite a good idea. Again, benefit having more people look over this project than if it was just closed. So one other thing that I've added before are these heat set embedded nuts. See what or threaded inserts. What you have here are basically a brass insert. You use a soldering iron or something hot to press into the plastic, and then you can screw and tighten things down into it. You'll need 2 for the tray if you're using this tray and you want to lock it in place. You can also use them here for these are M2 size. You can use this for the camera module 3 mount, and you also need them. These are M4 to put them to I guess tighten down each of these back fittings onto the enclosure. So you can see this is what it looks like without them, but you'll need to add them if you're printing it yourself to make sure it's locked in place. So to put that on, then we use an M2 hex screw. And just tighten it down. You don't have to tighten it down too much, otherwise you won't be able to focus it later. And you could also do this once you're focusing it, or after you focus it, I should say. But that is effectively the camera hardware mounted. Next is the Raspberry Pi itself. So here again, I've skipped a couple of steps with the standoffs because it's pretty slow TV watching me do that. But the brass standoffs, again, just a 15 millimeter, I think, on the top. This is for the Raspberry Pi driver board. And then down here, just a short one to keep it off the plastic. Probably the other, while I'm here, there are a set of holes here to mount a power supply board. So just like this one here. So there's 2 different ways of making the owl. You can either use the driver board that my brother designed and sort of buy that off his website, I think for about £39. But if you want to use a relay board, you can use relay board, just anyone, any hat, I guess you can find online. And problem with that though is you will need to add the power supply and then wire that in, as you can see here. If you're using the Raspberry Pi 5, because it's a 5 amp input, you do need to supply power over 2 sets of 5-volt pins on the GPIO. This is all explained in the instructions on the GitHub repository. Well, that's the benefit of this hat, though, is that it combines all that together. So you have all the here transistor-based switching. So rather than relays, electromechanical, it's all faster and I guess nicer, less noise. So and also combines all that together. But first, we'll put this Raspberry Pi in. That should fit in there like that. Make sure the outputs for the USB and Ethernet are at the front. And then you can use either of course, nuts, I guess. I like using the actual brass standoffs because I think you get more grip on the thread and they can tighten down a little better. So I put those on. Another benefit of the YAO driver board is it's completely solder free. So you can get away with building the YAO without soldering, whereas this, you do have to solder to the pins and you have to solder this board up as well. So there's a few downsides to this, I guess this method, but the bonus is you don't have to use any bespoke parts. Everything here is off the shelf, designed for a whole range of different purposes. So that's the Raspberry Pi installed. The next part I find easiest is probably to put the this ribbon cable in now. One probably good thing to do, I won't do it here, but is to cover it with some of this Captain tape, or at least some sort of tape to make sure that when it threads through when you thread it through here on the driver board, that you won't end up rubbing through that and causing any troubles. But I'll put that, we mount it to camera input 0. So it should say cam/display 0, which is this front one here. And then when you do, make sure you put just make this right. I think it's this way. So you put these, the metallic bits, I think, facing towards the Ethernet. And that also means that these metallic side is in the right orientation to mount with the camera as well. So these should be facing out. So fit in. All right, so that's the camera cable fitted. The next part is installing the driver board. So use the slot on the driver board, and you actually notice this has that 6th set of connectors on it, and that's for the disable enable that I'll show in the demonstration shortly for the outputs. So that should just fit on the pins like so. And then just put these screws on the top, and that's pretty much it. Cut those down. If you have any questions about this process, feel free to ask them in the chat or over the sound. I'll be happy to answer them best I can. It sounds like Tam, I think, has done a good job in the chat as well. All right, so that's everything, mostly hardware complete. So it is a lot easier and faster than it has been in the past. Another thing I should mention about the driver board, I think you better see it on this angle, is the different pins we have here. Actually, maybe if I get another one. This is the older version, just without that 6th set of connectors, but everything else is the same. But what you can see here is there are a set of 4 pins, jumper pins here, and there's a set over here, and on this one there's a set of jumper pins here, which is for the enable. So going through them, these set of sort of 4 or 6, they let you choose between how you want to decide the control of each of the outputs. So at the moment, by default, they're all set to the GPIO, so the Pi. So if you have them over to the right-hand side, at least for me, that will let the Pi control them with the default GPIO pins. And the default pins are described just here. So number 1 is GPIO 13 or board pin 13, 15, 16, and 18. That's also in the software. But if you want to use different pins, you'll have to remove these pins here and make the connections yourself between the GPIO and this point. We also have a PWM control on this board as well. So that's the chip here. And so if you want to use PWM control for each of these outputs, so if you want to do, say, PWM-based spot spraying, then you can dump these across further up. This is probably the most important one, and I've made the mistake of telling my brother it wasn't working, but it was working. I just forgot to put this enable power pin on. So this just connects the Pi to the power supply just next to it. So you definitely need that one to make sure everything is running correctly. Make sure it's right around. Alternatively, if you want to power the Pi separately, say through the USB-C, you'll need to remove this for sure. Then the final set of these enable sets. This is a new one. I think you should be able to see it on the screen. Hopefully, might better focus. But this enable set will enable all the outputs. So by default, they'll all ship when we send them out to people. They'll ship with a pin over this, like so, because you only really need this input if you are to start using it, say, for section-based control, or if you want to enable or turn it on and off all the outputs with a switch that you've wired up separately. But if you don't want to use that, just make sure you have that pin across. A red light will shine when all the outputs are enabled. So if you're having a couple of issues, maybe getting it started, there might be the power pin. Make sure you double check that. If the outputs aren't running, maybe check all these pins here are correct. And then finally, if, say, nothing of the outputs are being enabled, just double check there's a red light here and this jumper pin is on. All right, so that's pretty much the hardware done. The final thing is the SD card. So on a Raspberry Pi, the SD card goes in here. The design is a little bit tight, but you can do it. So usually what I do is I'll flash this with the latest version of Raspbian. I'll save all the software, I think, for a later webinar, just because it's quite difficult to try and manage these 3 cameras plus screen sharing. But basically this SD card, once you've flashed it with Raspbian, you want to stick it in here. And then usually I use a pair of tweezers or pliers to get in the right spot. Or sometimes it works with your fingers as well. And so that's all the hardware added. You will need to focus it and also tighten each of these to make sure they're in the right spot once you've focused it. And also that flathead screw there. But to fit into the enclosure, we can either use this one here, which is the aluminium one. And what you do is you slide it in on the second rail from the bottom. So it's 1, 2. You'll figure it out though once it matches up with that the output, also the lens cover. But slide it in like that. Just make sure all the wires, once you have them, are in the right spot, and it should neatly fit inside that enclosure like this. And then you can put the lens cap on. So this has a glued-in piece of glass, and that will go on the front. And then on the back is where you'll put your back piece on. These, of course, are not drilled, but you can drill them to fit, say, a single output if you're just controlling one or multiple. And alternatively, if you print them, the 3D printed options, there's 3 currently, but it's quite easy to do lots of different types of 3D printing. The default connectors I've been using are these are Amphenol Fathom Lock, just because they're quite compact and also allow high current, I think up to 13 amps through particular connectors for the power. And also they're not too expensive, and they're quite nice to use. But this is, I guess, bringing this one back. So this is, of course, just all the hardware. You do have to wire, say, if you do want to add your solenoids or relays or whatever else you want to put on the outputs, you'll also need to wire it up to something like this, where you have your connector of choice. By default, phenol fathom lock, as I suggested, but M12 connectors, or in the past we've used Bolgan, and there's a whole range of connectors out there, and I think everyone has their own preferences. But basically, you want to wire up, when you do wire this up for outputs, you can use just a single, say, a signal pin or signal wire into the positive. So you'll see out, this is out, and then plus, wire that in there. And then the ground is taken through the board. So if you want to, reduce the amount of heat put through the board, I guess if you're using 4 2-amp solenoids, then that can sort of generate a lot of heat inside the board. So potentially you can add a ground or your own earth pin out here and then connect it up, which I have done in the past. But this is a little bit neater, and it's not often that all 4 solenoids are on. As you can see here, there's another outputs are wired up like that. And then this is the input. So this is the 12 volts, or up to 27, I think, volts in these pins. But that's what it looks like once it's all connected to the outputs. This is, of course, just how it's once all the hardware is sat on top. But that is effectively the hardware assembly. And I can just quickly run through the software on the GitHub as well, just to show you how to install that. But I'll, in future, I think, versions of this, I'll also do a software walkthrough where I actually install it step by step, and then I show you how to do it. I think for this live demonstration, I guess we'll just talk through it. So are there any questions on that? It looks like Tan's made a pretty good answering those questions. Yeah, thanks for sharing that paper. So that's some work we did with a honors student a couple of years ago, back in 2022, I guess. And yeah, so we found that performance declines with speed, of course, but the HQ camera, the global shutter camera, wasn't available at the time. And so the HQ camera performed the best, or out of the Raspberry Pi cameras. We also tried the AlgaCam as well, but that's a little bit hard to install. You'd need a whole range of different drivers. So just quickly, I can run you through the software installation. Again, it's a little bit easier these days. So let me share my screen. I think that should be, oh, there we go. I think that's just loaded now. So with the software, what you do is you can just, again, all that I've just talked through here will be in detail on the hardware assembly, and also hardware requirements are all listed for the Compact OWL, and the differences I talked about between cameras, and also what you need in case you're using the driver board or just the relay control board. So you keep scrolling down and go to the software. There's the quick method where you basically flash an SD card with one of our provided disk images. This is very old software, so I really should update it. There's something I haven't got around to just yet. I will do in the future. But the quick method doesn't work currently for the Raspberry Pi 5, so avoid this, which is why I put this up here. Fortunately, the detailed method for the Raspberry Pi 5 these days is much faster. Probably takes about 15 minutes, 20 minutes. So it used to be about 1 hour. I probably do need to update some of this. But to install it, firstly you have to flash the SD card. In fact, you can use the Raspberry Pi imager. It does a lot of this, take a lot of detail for you in terms of setting up, say, like the passwords and usernames. And then once you've done that, you take that SD card out that I showed and put it into the OWL. Boot it up, provide it with 12 volts through the relay control, the driver board, or through your own power source. You can also do this when it's not connected to anything, and just connect a screen and a keyboard. You want to remove some unnecessary software, but it seems that's actually been removed already. So I think this is an unnecessary step. And then to the, I guess, the most important part is where you start installing and setting up the virtual environments. Also, probably the most important part at the moment is this line here, called sudo rpi update, because unfortunately they made a bug when I was talking about previously of RGB cameras. So in libcamera, the libcamera library, sort of getting to the very technical stuff, but in libcamera library, they use a format called RGB 888, 8-bit RGB format, which is what the Raspberry Pi and what the software uses to make sure it's in the right format for OpenCV, which is in a DGR format. So they put the blue channel first instead of the red channel for whatever reasons. But in the old kernel versions, they just accidentally made that mistake and flipped it. And so if you don't run sudo rpi update, you'll end up with inexplicably and quite confusingly flipped red and blue channels. So make sure you run this. I'll keep checking as they update the kernels, and when it's actually made it to the latest version that gets updated in this line, I'll remove it. But until then, that's very, very important. Then you want to set up virtual environments. And so virtual environments are just a way of keeping all your packages for this Python and all the different software in one spot. This can all be done for if you just want to download eventually that disk image. But it doesn't take too long to install the virtual environments. You set them to load automatically through the bashrc file. Then you make that virtual environment and just make sure you call it OWL. And also very important is system site packages. So that means it will adopt or transfer the Pi camera to library into that OWL virtual environment. So that's really critical if you're doing any vision-based work with a Raspberry Pi and you want to create a virtual environment. At least that's the best way that I've found. Then the next steps, just to activate that virtual environment, so work on OWL. Then you pip install OpenCV, just check it's working. Down here, you want to clone this repository, and that just means copying it and saving it to your hard drive. And you want to save it to the home directory, I guess, which is what this line here does. And saves into a folder called OWL. That might take a little moment to download. And then you need to install all the requirements that come along with the OpenWeedLocator software. And that's in this pip install -r requirements.txt. Then you can check that it's all working, and you should do all this with no errors. And the final, probably most important part as well, is if you want to use this to start automatically, so you don't have to connect a screen to it. I use the cron tab, I guess, to basically put this as a job in cron tab, and so it executes on start. And it's a little bit outside of what I know. At least that's what I've read, and that's what I'm regurgitating. But you have to make sure that the OWL file itself, owl.py, is executable, and you have to make sure the boot and the boot wrapper are also executable, and then move the boot to this file folder here, and move the boot wrapper as well to that same folder. That just explains what's in those files. And finally, this is where you want to change and edit that cron tab, as I mentioned. And all you need to do is add that line, which you can copy on the left-hand side here. And then you can start focusing and start using the camera, just using either bash focus or owl, and then it'll launch, and you'll have the blurriness here, or otherwise you can just do it yourself and when you think it's about right. So what we have is this controller, as I mentioned. We have to switch it on first. And we've got power coming from a power supply just over to the right, but you can provide any, as I said, between 12 volts is ideal, probably what most of you have on farm equipment, but up to 27 volts is what's supported by that driver board. But just, of course, be careful of all your downstream. If that's not supporting 24 volts, then that will get burnt out. But right now, the owl is booting up, and we'll also turn on the treadmill. What we have is just little green squares on the treadmill, and it'll start out at 1K an hour. But you can see that, I'll stick that down a little better. And once we enable the outputs, you should start to see that light flick on as the green comes past it. So this is of course very slow, but that light is indicative of, say, like a nozzle, just because it's inside. There we go, a bit faster. say up to 8 k's an hour. And I might need to get some extra lighting. That is one thing, is lighting, because these are color-based algorithms. They do require a lot of, I guess, consistency in lighting. And so as we're approaching sort of afternoon lighting here in Perth, you do run into some issues with darkness, but of course this is inside and it's been set up to run outdoors on in full bright sun. As you can see, that is picking up each of those little green squares and activating this light to simulate a spot spraying action. It can detect very small areas. This is running at 640 by 480 resolution. So it's running about 60 frames per second inside the Raspberry Pi here. Just sort of in the front there, the corner of the frame. And then if you look further down, you can sort of see that controller and then those individual green squares. That's at 8 kilometers an hour. I just angle that slightly. This is at 16, which is unfortunately the maximum of this treadmill. But you'll see even at 16, it's still picking up those small green squares. So just on that slow-mo footage, I think that shows a little bit more. This is when they're spaced apart. So you can see that the light turns on and that line, if I pause it, this is in previous, like early in the day, you can see lighting conditions have changed a lot. That line is in line with the bar, with the light, and you can see that the light is turning on well in advance of the weed. So that would effectively where your spray line is. So that weed will be well and truly detected and controlled. But that's with about a 50 centimeter gap between the two. This is a much narrower, this is the same gap as we saw before, so about 20 centimeters. And you can see that at this speed, where it turns on, it's still in advance of the weed. So around here. But I do sort of have a little, because this is light, obviously spray doesn't move at light speed. And so I wonder how effective that was at this speed. But I think in the future as well, one of the projects I want to work on and develop is angling the OpenWeedLocator by, say, a few degrees or 10 degrees. And that way you can mount it in line with the nozzles, but then have it looking forwards to detect the weed. And also making that a little bit modular. And so say you put the angle in that you're angling your OpenWeedLocator at, and then it'll make sure that the right solenoids turn on when they should. That's just the slow motion of what we just saw. What's interesting to see is that these black lines here are the effective sort of actuation zones for the owl. You see the weed enters the owl, and only once it sort of reaches this point does it actually the light start turning on. And that's just the processing time required to analyze every frame and then turn that relay on. But that's effectively got everything that I had for you today. So it's been the assembly, sort of a bit of an overview, the live demo, and of course, always here to answer questions. In my email, probably the best contact is guy@openag.tech. If you want to get in contact with any questions you might have had. The repository as well, if you're not familiar with it, is github.com, Geezer Coleman OpenWeedLocator, or otherwise just search OpenWeedLocator and it should come up. And I guess how to support the projects. The best way to support this is through building one and then telling me what's wrong with it or what could be done better. Trialing it on your farm, always happy to support that. So if you want to send me an email and organize a time to chat about how it might fit in your farm, or just to get some more use cases out there and people trying to break it pretty much. These are more times it's broken than hopefully less likely it might break in the future. And then of course, sharing feedback on community pages with with how you've gone about building it. Maybe there were some sticking points, or maybe you had suggestions about which solenoids to use. All you have to do is just head over to the GitHub again that I was showing before, and the discussions tab, and then sharing your experience there is really, really valuable. And then now also starting to offer, you can start to purchase kits. I will open up a web shop, of online place to sell parts, just to make it easier for people to build them in the future. just to get a better community going. But the actual weed locator and the designs will always be available to build yourself. And of course, it's always sort of cheaper if you buy the parts yourself and then assemble it. But if you're interested in any of those enclosures that I mentioned, or any sort of half-assembled kits and controllers, then certainly let me know. I'm happy to try and build one for you and send it over your way. Thanks everyone for attending. I really appreciate the number of people that came along and the support for the project. So certainly stay in touch. All the best building your hours wherever you are. And yeah, enjoy the rest of your day or afternoon.